I remember learning a good number of things coming to these meetups, the ML meetup and all these things. So I really consider it a big honor to be able to speak here for the first time, actually. So I thank Paul and everyone who's organizing it for asking me to come and talk for a little bit. So what I would like to talk about today is text processing. So I've been thinking about text processing for a little while now. Been building a bunch of different things in different sectors for different groups of people. Just as a small 2-second background, I'm really a math guy. I was doing pure math for a long time, and then I went into the data science space and tried to become an engineer to some extent. So I did a lot of, behavioral modeling. I did a lot of financial modeling, and then in the last year plus, I've really ended up building a lot of things in the text processing space, and I find it a fascinating space that is open both in the research, in the industry, and from an engineering, from a statistics, from a machine learning perspective. There are just many, many things to do, many things to think about, and I don't think it's a space that's going to get smaller. I think it's just going to get bigger and bigger. So hopefully everything I'll tell you about is easy, and hopefully most of it is high performance, at least what I think of as high performance. But feel free to interrupt and ask questions. There'll be some time for questions at the end, and maybe a tutorial if I have the time, but please jump in. Okay, so here's the outline of the talk. I'll give a little bit of a background as to what kinds of text processing problems I was asked to solve, which were the most important in my beginning to think about the structure of these things, the structure of text processing, the structure of working with textual data in the world that we have now. Give a couple of examples of the major projects that I've been on and still on some of them. And then we'll talk about how I do these things and talk about some of the technical aspects, talk about the philosophy. I'll refer a lot to the Rosetta library, which is a library that Ian Langmore, who might be here at some point, and myself have put together. There's a number of other contributors as well. And it's really a text processing geared library, solving a lot of those types of problems. All right, so one project that has gotten me to think a lot about text processing and in general human-computer interaction with regards to textual archives or textual information is the declassification engine, which is a project at Columbia University. And it's a far-reaching project. It's in part with the Brown Institute, which is connected to Stanford and to Columbia. And it's run by David Madigan, who's a statistician, a well-known statistician. Well, there's Ian now. Say hello. And Matt Connolly, who's a professor of history. And essentially, the idea is to bring together computer scientists, historians, statisticians, and data scientists from industry as well as from the academic environment to build tools for historians to be able to interact with large archives. And in particular, the archives that they're looking at here are released government documents, so declassified documents, cables, telephone transcriptions, and so on and so on. A lot of the FOIA, Freedom of Information Act documents, and so on. So one problem that we end up thinking about quite a bit is the sort of cold start problem, right? You have a very large database or a database of some size of documents, and you, as a historian, need to go and look somewhere, right? And keyword search is not sufficient to solve this problem in most instances, because first of all, you don't even know what you're looking for half of the time, and even if you do, it's hard to formulate in a beautiful Boolean expression exactly what it is that you're looking for. And most historians, of course, don't have, amazing Unix and grep skills, so most of the Boolean expressions are really going to be disjunctive that they use. So one way to approach this problem is to think about anomaly detection. And anomaly detection in this case can be semantic anomaly. So for example, here's some basic results of an latent Dirichlet allocation topic model, which looks at cables emanating from different embassies and looks at the semantics associated with those cables and starts to look for some patterns, right? So one of the things that, this was actually a project that Ian started up, one of the things that you'd notice is that if you look at cables which spring away from the topic that they're mostly associated with, they turn out to be secret cables. Fine, cables that were originally classified as secret. Potentially this is an interesting fact, potentially it's not interesting historically, but this gives a way for people to start looking at things, right? You can start looking at exactly these cables or these pieces of documents that are bringing forth these results, right? So it's a way to start. Another even sort of simpler or more simplistic approach is looking at frequency analysis, right? So you have metadata that you're potentially extracting from the text itself, maybe joining from the metadata that you have, and you're looking at frequencies, right? And you're looking at spikes in frequencies. Maybe you're modeling, you're having like a Kleinberg model of the communication stream or something like that, which is going to be highlighting when things happen that you don't expect to happen, right? So here's a trivial example. There's a spike in October, first spike in October '73. That's the Yom Kippur War. You can pull up the cable. Of course, this is obvious to a historian, but potentially the other spikes are not, right? So that's sort of an couple of examples of anomaly detection. Another project that Ian and I were on last year was building a large e-discovery pipeline. And if you've ever thought about what lawyers have to deal with, it's a gigantic mess, right? Because what they generally get handed over during the discovery or post-production process is a large collection of documents. These are emails, contracts, memos, Excel spreadsheets, and so on and so on and so on. And these could be hundreds and hundreds of thousands of documents, and they have a limited amount of time, limited amount of resources before deposition, and they're supposed to be able to interact with the system without it being random, right? So one of the things you're going to end up doing is you need to be able to determine or give some sort of classification system which is going to pull out relevant documents. And the definition of relevant is up to them, really. So you're going to end up doing something like this, right? Some sort of a thing that's going to feed into a classifier. It's going to involve a bunch of cleaning, parsing, tokenizing, and so on and so on. And generally, you want these things to be pretty fast. These are not potentially online processes, but you want fast turnaround times. You don't want things to wait for days. You want to compute for days. And you also want to be able to experiment. You want to build things modularly in a flexible way. So, one of the big things you're going to be doing is feature extraction, right? You're going to be taking a document. You're going to be pulling out the signals you care about, the features, the tokens, whatever you want to call them. And one of the things you're going to realize really, really quickly is that if you just do this in a sort of loggerhead way, you're going to blow up memory, right? You're just going to have too many features. If your features are words, or even if you look at the word stems and so on, they just won't actually fit. And moreover, even if they do fit, they'll make your machine learning tasks really hard, right? So you need to think about either reducing these number of words or using some appropriate sparse data structure and associated learning algorithms. So, what are some typical machine learning goals that I've had to deal with in the last year? So classification, right? Document classification or ranking. Sentiment analysis, recommendation systems, right? A lot of these are semantic based now. Anomaly detection, like I mentioned before, communication dynamics, metadata extraction. This is a big deal as well. Sometimes you want to actually be able to get things out of the documents themselves, which means you're not doing any sort of statistics, but you're doing a large processing, parsing, extraction task. Network extraction, right? That's a big deal. Social network. Authorship attribution, and so on, right? There are many, many tasks. And sort of what does the general, very, very high-level flow look like? Well, you start with a corpus. This corpus might live on a hard drive, in a database, coming from an API, maybe a web scraping, whatever. You're going to be pushing that to something that's going to be processing the documents, tokenizing it, extracting features, hashing, maybe pulling out some metadata you want, maybe merging that with metadata that's given to you, and then you're going to be pushing that to a machine learning task, right? Whatever that might be. And this could be, there could be an active learning part of this. There could be, optimization, online optimization, many variants. But this is sort of the general, very basic framework. And so what is actually hard about text processing? Well, in order for this thing to actually work and run, you have to think about data structures and generally use sparse data structures because things don't fit in memory. It's language, right? Language is difficult for pretty much the obvious reasons. The actual parsing and feature extraction can be really radically different from one collection to another. You know, something a legal team is going to give you is going to be completely different from, like, you know, a collection of web pages, right? It might be even difficult to get these things into machine-readable format, right? Sometimes part of your process might be identifying the original encoding of the document or identifying the original format of the document, right? You might have a database dump of just .txt files where some of these were Excel, some of these were Gmail, some of these were memos, and you have different processes for dealing with that. And a lot of the sort of software development has been geared towards, you know, huge data drives, huge scalable distributive systems, Hadoop, and all of these things. And for the most part, this isn't the problem we're trying to solve, right? It's not a Facebook problem or a Google problem. It's really a problem with dealing with a fairly stable collection in particular, right? A database that maybe doesn't grow that quickly or maybe doesn't grow at all, and providing tools and being able to process that in a fast and agile way. And there also isn't really a simple solution in the way that there is one for the numeric stack, right? Numeric processing, we know how to do that. If we want to do machine learning in Python, let's say, we know we can take sklearn, we can take pandas, we can take NumPy, we can take STAPS models, and we have a nice collection of tools. If we think about text processing, you know, what is that collection of tools? So it's something to think about, and that's what Ian and I were thinking about when we ended up putting this library together. And what's fun about text processing, well, they're pretty much the same things that are hard about it, at least from my perspective. And you have to care about memory, so you have to care about engineering and processing speed and all the things that come with NLP. And if you're a Unix fan like I am, you get to do quite a bit of Unix, and Python is really nice, although Python isn't exclusively the nice language for that. And then you have to, whatever ecosystem you're in, you're probably, whether it's, I'm going to do most of my examples in Python, but pretty much everything applies to R and to whatever it is that you use, you're going to end up stepping out of that ecosystem. So you have to think about how to do that in an efficient, testable, scalable way as well. So the first thing is, you know, what's the first thing on the agenda? Well, dealing with limited memory. So how do you deal with limited memory? Well, you know, there's the hardware piece of it, which means, you know, what machine do you want to use? And my answer to that is that, you know, don't think about clusters, right? Don't think about, you know, a highly distributed system that you have to manage, that you have to deal with the actual distribution with the over the network you create, and so on and so on. A lot of the solutions, if you write code well and you optimize the code, can be solved on much cheaper, much simpler machines. Like Ian did a lot of the work on his System 76 laptop, which is not an expensive laptop, but it has really nice hardware, right? You can do it on this, which is much more expensive and has about the same hardware. Or you can buy, you know, like at some point we needed something just slightly more powerful, and we just bought a machine which is upgradable. It costs like $6 to $7 grand. We stuck it in a closet with lots of fans. It was still too loud, and then we put it down in a server center, and that basically took care of all the problems we could envision for a while. And we weren't dealing with small data sets. Or you can go AWS or DigitalOcean or any of these things. So, you know, if you do just very basic, you know, back of the envelope memory calculations, you know, if you think about how much memory text is going to take, if you put it in your CPU, it's going to take pretty much the same as in your hard drive. It can take more. So one obvious thing to do is to hash everything, right? I mean, if you think numbers, you know, doubles take 8 bytes, right? So 1 million doubles will take 8 megabytes, and so on and so on, right? So you can save a lot of space just by using the right hash map or the right, even the right data structure, which we'll see in a second. So, and the other thing we do quite a bit is from a philosophical perspective, we monitor memory a lot, and we think about that all the time, and we monitor with things like HStop, and which doesn't work on this computer, and iStat. By the way, HStop does work on Macs, but it has a tendency to give you the wrong results. But there are other solutions. But just consciously thinking about that in all your processing and all your code writing actually helps a lot. It might sound banal, but if you commit to it, it will help. And the other thing is that a lot of the text processing tasks, if you actually think about it, are not memory-intensive tasks, especially the tokenization bit, right? Because realistically speaking, what do you care about? You have a gigantic collection of documents. You don't actually care about the collection of documents. You only care about the tokens or the features or the signals you're going to extract from them, right? So essentially what you really want to do is you want to just take this collection and you want to transform it into whatever it is that you want to use. And that transformation is pretty much, once you've set it up, once you know how to do it, you're going to take all the words, you can take all the nouns, you're going to step, whatever it is, you're going to take the first letter of every word, whatever it is that it might be. The actual entities themselves, the documents, the process is independent of the different documents, right? You can feature extract on one document and feature extract on another, right? So one of the ways to do that is to stream, right? Or even if you have a very large document, you're dealing with 19th century romantic novels or something like this, you can stream these things line by line, right? Which means that you never keep anything in memory, right? And you're always writing to standard out, you're always writing to disk, you're always writing to some sparse data structure that you care about, right? You do this file at a document at a time, file at a time, line at a time, or combinations thereof. So, and the other thing is just think about the sort of machine, once you're thinking all the way through to the end of the pipeline, think about the machine learning algorithms you're going to use, right? What's the sort of nice equivalent of streaming? Well, machine learning algorithms that use stochastic gradient descent. We'll see an example of LDA topic model, which uses, which is implemented in a library called Vopal-Wabbit, which does exactly that, which is much, much faster than the other implementations. So, very, very basic summation of dealing with limited memory. Just stream as much as you want, as much as you can, and then deal with huge feature counts by sparse data structures, stochastic gradient descent, or just to reduce the number of features you care with off the bat by doing intelligent things like throwing away stop words or throwing away things you don't really care about. But don't put everything in memory. Only keep in memory what you need at any given moment. So this is one of the reasons a lot of times you don't really need very big, very powerful machines, right? Because it doesn't matter what your memory is. You're keeping very little in there. So what about making things actually faster? Well, one of the generic goals, as I mentioned, is tokenizing, right? So tokenization, if you haven't done it, essentially is going to, as a very simple example, is going to be taking some sentence, getting rid of the things you don't actually want, and leaving the words you care about, right? This could be a much more involved process. It can involve quite a bit of NLP. You can be using, you can be part of speech tagging. You can be STEMI. You can be lemmatized. You could be taking bigrams. You can do many, many things. But essentially, what you're going to be doing is taking some string and breaking it up into a bunch of other strings, which you might have. So, for example, here, here's a sentence. Let's do a deal, trade some money, and the words you care about are those. Okay. So, how would you do that? Well, you might write a very, very simple function like this, which involves a bunch of for loops, right? And then some cleaning up, right? So it throws out your stop words, it takes care of your punctuation, takes care of your text. So you might think this is perfectly fine, but then you go off and you test it and you see how long it takes, right? Well, this is, a pretty serious amount of time this thing is taking to run, right? So you time it. This is a nice Unix utility, time, right? We use this all the time. And so you go and you say, well, this is never going to work for me because I have to do this, 10 million times or something like that, right? And the documents are fairly long. So you start optimizing it. So you start to think, how do I make it faster? Well, maybe you want to switch to a regular expression, right? Regular expression in Python is a C-based library. It's optimized. It's fast. You do that, okay. You test it again, right? You get something faster. Or if you want to be a bit more pedantic and actually do something that will tell you exactly what's happening to your code, you can line profile it. R has nice line profilers. Python has really nice line profilers. They'll tell you exactly how much time is being spent on exactly each line of code, right? So if we look at our now second version of the tokenizer, we see that most of the time is spent on the on line 62, right? And then after that, most time is spent on line 61. So we realize that something is slowing us down, that if we do this if statement, we do a check, what is actually happening? Well, we think about how to make that faster. Well, one obvious answer is to think about data structure, right? Or what objects you're going to use. Stop words as a list, right? So what do? Well, one easy thing to do is replace that list with a set, right? A set is a hash. You don't have to do, it's a much faster lookup. And you reduce your time just by doing like a trivial change. And the reason you knew how to do that change is because you profiled, right? And these things become incredibly important when dealing with large collections of text, because essentially these are the things that are going to make you, take 1 minute or 10 hours, right? So here's a basic example of the two options, right? So one is using set is significantly faster, right? I mean, you can see the result, right? And we use different utilities. You time Unix time, or you can time in Python. Here it says time at do 250 loops, or and here you see the time. Okay. Cool. Yeah. What's up? Yeah.
When you have classified files or data, you know that every time that you turn to asset or again it's redacted, the same document. So the machine learning tools that you have notice that pattern when you do frequency analysis or no?
Sorry. So your question is about how going from the collection of text to the classifier. I mean, so the point is that you try to never return to the original documents, right? You try to do things in an online and a stream fashion, right? Where you're processing things, once you process the document, once you get everything out of it you want, you hashed it, basically.
No, I mean,
Yeah.
the same document, you can, every year they try, if it's a new or old document, they're trying to redact it. Every time they redact a different version of the same document, do the machine learning or the frequency analysis notice that?
I mean, I guess that's a very specific question, right? You're asking like, the question is, what happens if you have a collection, right, and the collection is somehow updated, the actual individual documents in them are updated? How do you deal with that? Well, I mean you do notice things change, right? I mean, that I get, maybe if I'm understanding your question, I mean, like it really depends on the task, right? If your task is to be able to identify, it's going to be very different. Identify change is going to be very different if your task is to tokenize into a bunch of words and then classify, right? So you're going to have a different process. Yeah, with government documents, that's actually a big deal, and we do work with multiple versions of the same document that has been redacted over time. But a lot of that problem is an OCR problem, is an image recognition problem at first, because you don't even know where the redactions happen. So that's a completely different story. Yeah.
Have you ever dealt with extracting bigrams or n-grams from text?
Yeah.
And say there's a stop word, like if it's a phrase or an idiom, and there's a stop word in the middle, have you, like, I don't know, if you figured out a way to like optimally extract those features?
So basically what you're saying is that suppose I want to tokenize a piece of text and I'm interested in bigrams, right? So these are tuples of words, right, that are next to each other. However, I have a collection of stop words which I don't want to be part of that, right? Or you want it to be sensible. I mean, one way is that you can also just drop them, right? You can always drop them from initially, right? And then you can put your bigrams together, right? Or you can consider that a break, like a sentence break. So you could split on your stop words first. Does that make sense?
But say if it's like a trigram, which is like a string of 3,
Yeah.
and then there's the word the in the middle.
Yeah.
That, I mean, the phrase is only meaningful if the is there.
Yeah.
And there's two other words there, so do you have to just sort of brute force it?
I mean, I guess it just depends on the context, right? I mean, I don't know. I don't think there's going to be a canonical NLP answer for that, right? It just depends on what you want to do. But a natural thing to do would be just to split on those, right? Because in the end, like, it also depends on how often that happens and how much you actually care about what the language is saying, as opposed to you just want to be able to group things together and see if these are grouped like this and they appear here, and they're grouped like that and they appear there, then that's statistically indicative of something, right? That's what you want. Like, you're also going to be running the same process hopefully of tokenization on the entire corpus, right? So whatever is going to be creating the signal stream that's going to be going into your machine learning bit is going to have the same process on the front or on the back end of it. So that is going to be uniform. So yeah. I mean, I think a lot of that is just going to come into some sort of, exploratory data analysis phase, right? Where you have to start from somewhere, right? Unless you have absolutely no choice, and you know that you will not see any of these documents until you have to tokenize them. Imagine it's just going to be like you have to go now, and somebody's like, "Here's your API. Just start hitting the API and start optimizing this recommendation system," right? There are cold start problems like this. It's not crazy, right? So then, okay, then you do your best tokenizer guess, which is like the simplest one. But generally, like when you're dealing with a collection, you get to see it. You get to do some exploratory. You can do some NLP on it, right? There's something that's going to feed it. And everything we build, we have, there's the NLTK tokenizers. There's the Stanford library. We built some optimized basic tokenizers because we just thought the NLTK ones were very slow. But the way we write everything is that the tokenizer function is just a parameter in everything you do. So you write the tokenizer function that's custom to your process, custom to your language, right? Yeah.
Any performance issue when you tokenize on original documents?
I mean, the performance issue, there's a question about performance. The performance issues are really just going to come from the task at hand, right? But the philosophy is that the tokenization bit shouldn't have performance issues, right? Because you can tokenize one line at a time, you can tokenize n characters at a time, you can tokenize one file at a time, right? So as long as your tokenization bit isn't slow, like as long as you've line profiled it and you've gotten it to the best you can, maybe you got the best data structures, you wrote it really well, maybe you use Python, maybe you use whatever, you see anything you need, right? As long as that bit is fast, everything else shouldn't impede its speed, because everything else is completely parallelizable, which we'll talk about in a second, right? Are we good? Okay. So just back to that. So you could profile more. You can say that you can see the speed up, right? You can see where your problems might be, right? So you can just iterate on this process. You can put a list comprehension, which is going to be faster because it has a fast append. It's like a loop, et cetera, et cetera. It might look nicer to you if you have some sort of aesthetic disposition towards code, and then you time it for total time and so on. I'm not claiming that this example here is some sort of an optimized tokenizer, but this is the sort of process we do all the time with everything. Like every bit that you're going to use, right? Before it gets fed into the pipeline, the stream, before it gets parallelized, we try to do this sort of stuff with it. And then think about the data structures, right? Because you have a lot of really great languages in Python and R. They're really powerful and so on and so on. They have all these brilliant, convenient, high-level data structures, but some of those come with huge overhead. List lookup versus set lookup. Python dictionaries doesn't allow the compiler to allocate, memory in blocks right next to each other, right? So, it's going to be inherently slower. A lot of the time, you might use a more lightweight or simpler data structure, which you can create yourself, right? You can just write a class. Here's my data structure. This is all I need, and it's going to tell the compiler how to allocate memory more intelligently, right? In the way you would do it in C or C++. Right? There's a really nice blog post about this that's just, I think, right on, which you can see here. By the way, the slides will be available and with all the hyperlinks inside. And the other thing is, of course, as I've mentioned this a number of times, is that all of this is streamable, all of this is parallelizable, right? These documents have nothing, a lot of times have nothing to do with each other. The API calls might be completely independent. The web pages are independent. Everything's independent. So you do this completely independently, right? So in theory, it's infinitely scalable. And so you just have to figure out how to do that. So in Python, and there's a really brilliant library, the multiprocessing library. In R, there's also really nice multiprocessing libraries. I haven't coded in R in a little while, but I certainly remember using them from a year or so ago. I'm sure they're better now. And so here's an example of a parallelized process that spawns 4 subprocesses. It pickles our function and iterable and pipes them to side process, right? So it's this is just a few lines of code, and we've parallelized it, right? So we can run it on in 4 streams in parallel, right? So there are certain issues that come along with that, right? You don't really get everything for free when you can't just hit something with a multiprocessing library of sorts and just hope it all work, just like shove functions into some black box and iterables or lists or whatever. You have to think about it a little bit. So, for example, what happens if your function isn't one variable, right? But you're trying to parallelize over some iterable or over some list, which is one of the variables in the functions, one of the arguments. The other thing is that this thing depends on pickling. Pickling is not possible for all functions, so you have to think about that. And the other thing is that, what does that mean to debug, right? So we do quite a bit of debugging. So, I use Python PDB, PDB++, and so on and so on. What happens if you have a parallelized process and you're trying to debug, right? That's not really possible. So, so it kind of sucks if you're going to be writing code, which you have to write some other code in order to debug the code, and then you parallelize the code, and then maybe there's something broken, and then you still can't step through it, right? Et cetera, et cetera. So the library is nice, but there are things you need to think about. So some of these problems are easy to solve. For example, if you have functions of many variables, you can use partial, which is essentially a wrapper. It's almost like a decorator. It returns a function of the variable you care about. So here's an example, right? You have a function of 2 variables, a and x. You define your function of a, which is a partial, where you set a to 3 in this case, right? And then you can parallelize that, right? So now you've fed function a an iterable, which is this list of 4 things, and or 3, and you're able to easily parallelize it well. Some things are a little bit more involved, especially dealing with pickling and dealing with debugging. So a lot of the work that Ian did on the library had to do with giving you really nice tools to be able to do that. So there's a function in the library, in the parallel submodule called mapeasy, which tries to pickle your function, which means it throws the applicable error. It allows you to set the number of jobs to 1, which basically is like not parallelizing at all, which allows you to step through it with a debugger. So you basically set it to 1, you debug, you do everything you want, you set it to -1, which means use all the available CPUs or whatever you need, and then you're good to go, right? And allows you to exit with Control-C, which is a nice thing, I think, without shutting down your whole shebang there. There's a whole bunch of other things you might want to think about in terms of parallelization. You can look at IMAPeasy, which is which allows you to send out jobs and return chunks, and so on and so on. So I would just say take a look at Rosetta Parallel. There's a couple of things that will make your life, I think, a lot easier, especially in the text processing world, but also in general. And so the summary of making things faster is, well, if you're in Python and you're dealing with, or in Unix and you're dealing with extracting text, use regular expressions, right? Use the right, because they're fast. Use the right data structures, NumPy and pandas for numbers. Maybe write your own data structures. Think about when you want to use sets versus lists versus whatever, right? Profile your code as much as possible. Profile it in Unix with time, profile it in Python with time-it, line profile it, and so on and so on. Use multiprocessing, whether it's the multiprocessing library from Python or the functions that we wrote for Rosetta. And just note that, I might be talking about Python because this is just a convenience for the moment, but pretty much everything here is completely relevant to most of the environments you work in, right? It's definitely relevant to everything I've ever worked in. Yeah.
Can you talk a little bit more about debugging, specifically in terms of large data sets? A lot of the
I mean, you're saying that, so the question is what happens if your bug is thrown by some document that is, you know,
That's right. I'm interested in any tricks you have.
so
So keeping track of where you are.
yeah, so that's actually a decent question in general. So that might earn you a book. The 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 point is that a lot of the time, so if you're thinking of a one pass scenario, right, you don't want to pass over many times. You actually want to keep information about what you've passed, other than whatever the tokens, other than the hash, whatever it is, right? So we wrote all these streamers which allow you to cache whatever information you want, right? So if you allow if you allow for your tokenizer or whatever function your streamer to say throw an exception to accept some sort of an error, you can have that doc ID be cached, or the file number, file name, or whatever it is, or line number, whatever information you're expecting is necessary for you to get to where you need it to be, can be actually cached inside the streaming process, right? That's also a lot of ways how you might extract metadata, right? So imagine you have you're doing a gigantic directory crawl, right? And you want to tokenize every file, every text file in the directory, but you also want to keep all the creation times, and you want to keep all the formats, and you want to keep all whatever it is that you want to keep, right? And you don't want to do that twice, right? So you cache all this information along the way, and you want to cache potentially bad doc IDs as well, right? Somewhere where there's an exception that's thrown, you cache that in, and then you deal with that later.
Right, so I mean, if it throws an exception, then just make sure your traceback is informative.
That's right.
And if it's
Right, but the question is might be like I don't want to stop everything, right? So which means you can write functions which will catch that exception and cache whatever information you want along the way, like throw it into a file or cache it in the streamer class.
To what degree is like just the basic I/O, like file system I/O important?
To what degree is the file system I/O?
Yeah, I mean, like, because on most systems, like the I/O is the slowest aspect, like reading a file
Yeah.
versus like in-memory processing.
Yes.
So with like SSDs or something.
Oh, so when Ian and I built that machine, or had someone build that machine for us, because we don't know how to build machines very well, we bought the best SSDs we could get. Basically, that was one of the things, right? I mean, I don't remember what we bought exactly, but we bought some really nice rated SSDs because we knew that this was going to be the problem we were dealing with. We cared more about that than we cared about CPU. The thing had 64 gigs of RAM, but it was totally upgradable. But we didn't know when we would upgrade it. We cared more about CPU, disk I/O than anything.
yeah, for things like local web, it's entirely bound by I/O, and then for other yeah, so like a lot of the online learning algorithms are bound by I/O, so that's your only bottleneck.
Yep.
That's important.
And you can get, I mean, like, if you want an online, like DigitalOcean, which is a cloud service, has really great, cheap machines. The price is cheap, but the disks in the machines are really nice. They have really nice SSDs, right? So you don't need to build the thing yourself, right, or buy it. You can actually, for $10 a month or $20 a month, you can have a pretty nice machine to your disposal. Yeah.
But mostly, if all you do is sequential reads for the streams, why do you care about I/O so much? It's just the speed that makes you to like communicate with data from the disk. I don't think it's ever really an issue.
Yeah, it's typically slower than
The operating system caches it anyway, right? If you have enough memory, you're gonna get cached read ahead.
I mean, you care about how fast you're able to read from the disk.
Yeah, but if you do it once,
Well, but if you do it, I mean, you're not doing it once, right? I mean, you have you have a terabyte of data. You got to read it. It's going to make a difference whether it's some crappy spin disk or it's going to be a nice SSD.
You can also do things like, pre-processing a lot of stuff. So you pre-process your tokenizing, and then you store that somewhere. It might take more disk space, but you're not going to have that much in memory, so you can shuttle that back and forth.
I mean, there's a lot of tricks. That's right. I mean, there's a lot of tricks you can do to try to optimize this process. You know, whatever it is you want to get out of it in the end, right? That's really the question. The point is that the philosophy is just to stream, to parallelize, to never worry about memory, and to optimize what it is that actually does the processing itself, right? Whether it's with nice, you know, with nice software, with nice hardware, and so on. Yeah. I mean, there are no, we don't really we deal with disk issues, right? In the sense of like a hardware person would, right? We'll just work with whatever is at hand. I mean, all I know is that if you buy better SSDs, you'll see better performance for this sort of stuff, right? Especially things like, you know, like Wopo Wabbit, which is the LDA piece of software implementation, which is all disk I/O bound.
You have to bear in mind that SSDs has a problem that if the hardware get damaged, there's no backup, you cannot get it back. So
I mean, you can always RAID everything. Everything can be backed up.
into a regular
Sure, but it's a different problem, right? I mean, it's not the problem we really want to think about at the moment, right? We can think about, you know, we think about what the right optimal machine is for a given scenario, but there is ways to back everything up, right? To an extent, right? But sort of the culmination example that I wanted to go through, and hopefully we'll have time to see it in a step through tutorial, is one of the things that we play with a lot, which is LDA topic modeling, and this is a statistical approach developed by Blay and Eng and Jordan about 10 years ago. I think they released their paper, and it's a hierarchical Bayesian model. And what it attempts to do is attempts to describe the underlying semantic structure. And the way it sort of does that is that it sort of imagines that you have a distribution of distributions, right? Where each distribution is a topic, right? So by topic, what I mean is a distribution of terms. So every document in your collection is some sort of a mixture of distributions of words, right? So one way to think about it is that, you know, a convenient way to think about it is to think about these things as topics, even though they might not be meaningful in terms of, you know, human readability. But what you can imagine is that, suppose I have this gigantic corpus and I have an oracle which is generating text. And the way this oracle is going to generate text is that it's going to first generate a distribution, a randomly choose a distribution of the tokens or the words that I see in my text. And then from that distribution, choose a word, right? So you can think of every single document as some sort of a mixture of these randomly chosen distributions of these topics, and then the words that appear with a given probability or a given weight from these distributions, right? So this is not a spectacular explanation of LDA topic modeling. It's kind of a more or less involved statistical bit, but essentially the two things you have to worry about is that there's a parameter that's going to control the distribution of these topics, right? These kind of groups of words, right? You can think of about these topics as essentially ways of saying, you know, this document has these groups of words, and within each group, we have certain words appearing with certain weights or certain probability frequencies. So there's going to be a parameter that's going to be controlling these groups of words, and there's going to be a parameter that's going to be controlling the actual word probabilities themselves. And as an aside, this has, you know, the LDA topic modeling has very little to do with text processing per se, except the fact that it was motivated by it. You can use it in all sorts of different scenarios that have nothing to do with text or language or any of these things. And one of the things that we like the Wopo Wabbit implementation for is that it's an online, you know, gradient descent learning algorithm, right? Which essentially means that it's written well, right? It's optimized C++ code. There are other ones. There's a nice library called Gensum in Python, which is really, really nice. But you're going to have a lot of time to wait every time you want to do something. We're talking about, you know, something that might take 10 hours in Gensum might take, you know, a minute or two in Wopo Wabbit. And this is the reason that it actually works fairly fast. However, there's a caveat, right? Gensum is really nice because it's a Python library. You pip install it. You have nice ways to interact with the data, pipe the data in, get it out. Everything is Python local. Here you have something completely different, right? Completely different. It's a command line interface. input and output of the files, the form of the files that you need to feed in to WopelWabbit, the format that it spits out is something that's not immediately usable, right? It's not a completely trivial thing. You can't just read it into a pandas data frame and say, oh, I know what I'm looking at, right? So one of the things that we decided to do is that we would in scenarios like this, if we wanted to stay in the Python ecosystem, we would write bindings that would allow you to easily transform data to this format and easily read the data out. But everything else would remain there. We don't write, you could, of course, write a subprocess call, which would call the WopelRabbit utility on the command line. But essentially, all we really care about is we don't mess with the outside ecosystem piece of software. All we allow ourselves to do is essentially to have a nice way to interact with the data structures that it requires and the data formats it requires. So here's just a very fast walk through. We have these text file streamers, which allow you to write stream files from a certain directory that are totally parallelizable, that allow you to take whatever tokenizer you want, create your own, use NLTK. We'll see that in a second, and stream that to a WopelWabbit file, right? You can also look at that. You can look at the output. You can do all sorts of nice filtering things, like throw out the words that don't appear too much, throw out the words that appear too often, et cetera, right? And then you go back to your Unix shell, or if you really care, you go system.subprocess or whatnot, and then you run WopelWabbit, and then we have a nice way to interact with the results, right? Here's what sort of a WopelRabbit format file will look like. We'll convert it to something that looks like that, right? So this isn't, I'm not saying you should go to Rosetto to use WopelRabbit, but this is just a nice philosophy to do with this. Like stream and then stay within your ecosystem to do the things that you like to do. Don't try to wrap everything, right? So I'm just going to go right to the summary, and then we'll just do a short demo of exactly what I've been talking about, which I think is going to be worth more than the words I can bring. So what's the summary of the entire story, right? So you pay attention to memory, you pay attention to data structures, you profile for performance. Your parallelization is really, really easy for most text processing tasks, right? They're independent of each other, the actual entities, the documents. Use Python to make your life easier, or use whatever it is that you use, R, C, when you step out of the ecosystem, to make that easier. Don't wrap everything in some awkward way. And don't forget about command line utilities, which we write quite a bit of. And don't forget about Unix, because it's really, really good. So I'm just going to jump to the demo, so you guys have questions. How's that? Yeah, go ahead, man. Anomaly detection? Anomaly detection is just an example of the types of things that we end up doing quite a bit with text processing, right? It's just an approach that I like to think. It's a paradigm that I like to think about when trying to give, for example, trying to give people access to a large collection they've never dealt with. Right? It's like doing a cold start problem in archival research, right? That you end up doing that, right? I mean, you have in that example historians with millions of documents to look at. They don't know what to look at, right? They don't know where to start. What's a nice way to start? One nice way to start is anomaly detection. There's something is going on, whether semantically, metadata-wise, frequency-wise, or whatever, right? And once you're there, then you can think of other tools, right? Then you can try to imagine how you would allow people to find documents that are related or associated to this given scenario, right, if they care about. That's a slightly different, that's a next step problem. But that's really why I brought up anomaly detection to begin with. So.
Well, I'm asking this, you can imagine anomaly, you have to define what is normal and not normal.
That's right.
You can be very sophisticated in your definition. And if it's sufficiently sophisticated, you can define a lot of possible kinds.
That's right. Yeah, I mean, anomaly detection is exactly that. I mean, right, you have to define what's normal, and then you have to see what stays aside of that. But it's a paradigm, right? It's not a well-defined process. Right? Cool. Questions? Yeah.
When you're reading
Well, I mean, a lot of that's an operating system problem, right? Well, you don't have to. The question is, how do you make sure that two files aren't read at the same time? So for example, if you are passing an iterable or a list, right, and that list is a bunch of paths to your file, which are given by some directory crawl, right? It's going to pass different file paths to different processes, right?
So it's sort of like you can get the paths in serial and then break up the paths into separate chunks and send each of those to separate processes.
That's right. Or lines or whatever.
What about the writes though? Are you writing back to the same log file?
But I mean, the operating system handles writes, right? So hopefully your operating system actually works, right?
Block each other.
Right. But I mean, that's not going to happen, right? Yeah.
Going back to your latent Dirichlet, wasn't there other hyperparameter, correct me if I'm wrong, I'm not on your level, at the theta? I mean, don't you also have to, besides your alpha, besides your ROR, wasn't there also a theta that has to be on an a priori? I mean, for
You're asking if there are other hyperparameters which are necessary for LDA topic modeling? Yeah, but I'm not going to get into that. Yeah. Go ahead. Sorry. No, it's
Early on at the beginning, you mentioned network extraction.
yeah. So, yeah, so for example, one of the things that people are interested in at the classification engine in terms of network extraction is finding out who was talking to whom when in these, say, government declassified, who was talking to whom about whom, right? In these government cables, in the telephone transcriptions, and so on and so on, right? So that might be a simple problem, like, because you might know who sent the thing, right? Or it might be a more involved problem in which it is in that particular case, because you're trying to actually extract the names themselves, right? And you have to make sure you're extracting actual names of people, and also you have to make sure you are matching different versions of the same name to the same person, right? So Henry Kissinger and H. Kissinger, and some misspelling of Kissinger is going to be exactly the same, right? So then you build a network of who was talking to whom, how, and when, and in what frequency, and then you can analyze the dynamics there.
What about the context of the phrase or however you tokenize things, being able to look for those kinds of connections?
I mean, at least in that particular example, the network extraction is slightly, it's a different problem from the tokenization problem. Meaning that, or you can think of it as a tokenization problem where your tokens are names, right? So your tokenizer drops everything except individual names. And then not only does it drop everything except individual names, it puts all the aliases for the same name together, right? That's your tokenizer function. So it's a problem in its own right. But this certainly, the paradigm of stream, tokenize, and do, write that to somewhere else is perfectly in line with that process. Cool. Okay, so let's step through this. So this is all joint work with Ian, who's over there, and it's all in the Rosetta library, which has had a release a few days ago. So let's begin, right? I don't need to do the introduction. We've already talked about pretty much everything. So let's import. Let's talk about streamers. These are just directory names, so I get the right files. This notebook is available in the library, and I can give you the data set if you care about it. But it's pretty much will work with any collection of text documents, right? Just replace the directory name to what you want, right? So here's a simple example of a streamer, right? So here's a simple file streamer. All it's going to do is it's just going to yield the text of a file, right? So let's just look at it. Like, what does it actually do? There's a utility we wrote which gets all the paths, in a given directory, or actually crawls all those subdirectories as well. And then for p in paths, what it does is that it opens the file, right? It gets the text, f.read, and then it yields the text. And the only thing you have to notice about it is that this is actually, it's yielding, right? It's not returning, which means this is a generator function. This is not a regular function in Python, which is, and generator functions are really quite amazing and quite powerful. They essentially create a .iter and a .next method, so they allow you to create iterables, right? Which is what we use extensively for everything. But I would just take a look. But so if you wanted like a very, very small example what a generator or function or your iterable would look like, so just see what happens here, right? So I have an iterable here which is supposed to do some things until it gets, it's supposed to print a number until it gets to the nth number, which you feed it, in our case 5, and then it's supposed to stop, right? And when it stops, it raises a stop iteration, right? So here it is, we're printing, and then bam, it raises a stop iteration, right? So, right? However, if you feed that into a for loop, so what is a for loop, which you've been using for quite a while, essentially what it does is that it waits for that stop iteration to happen and then finishes the process, right? So you've been actually essentially been using generators and iterators implicitly if you've just been writing for loops, okay? So let's just set up a simple stream, right? So what is it going to be? Oops. So here's our simple stream. What kind of an object is it? It's a generator object. Great, and let's look at what it's going to do, right? So, okay, it's just streaming all the information about the files that we have there, right? Splitting them, split line, just that it's easier to read, right? So you can see these are government documents, okay? Cool. So let's import a few more things from Rosetta. There's a nice object in the method in there in the streamer classes called InfoStream, which essentially allows you to stream whatever it is that you want. If you want to be able to tokenize and use the tokenizer methods, it has to stream something with a text key. But you can put whatever you want in there, and as we talked about before, you can cache these things along the way, right? You can throw in, you know, Unix timestamp, creation stamps, and cache them along the way, and so on and so on. So it's just a convenient way to sort of organize the information that's coming in. So for example, here, if you look at just stream.next, right, it's new things are happening. So we're caching a path. We are caching the creation time, the document ID, modification time, size, the actual text, and the tokens, right? Things that might be useful if you don't want to pass over the data twice, right? Which is one of the things we won't care about. Okay, and if we want just the text, right, we can just see it here. Okay, and that might be what we're actually going to be tokenizing, right? So. So if we want the tokens, so here I'm using a very basic tokenizer that we wrote that's part of the library, which you can use whatever you want. You see, right, we're just producing, calling .next, it's producing the tokens for the next document. Right, but you can use the NLTK tokenizer if you want. You can see it'll produce slightly different things, allows for more numerics, because one of the defaults is no numerics in ours. Okay. Cool, now we get to some of the Vopowabbit stuff, right? So we ran on 1,000 documents. If it was, if the data set was a little bit longer, you could have seen it blow up my memory here, but it's pretty small. So we just created a Vopowabbit format, tokenized format for all the documents in the collection, right? Can run, I'm not going to run this in command line, but you run that in command line. It takes about 2 seconds in this particular case. We load the file, right? This is all in Python. And then we can get to look at what's actually happening, right? Okay, so we're seeing, these are the words we see. These are the counts, the token score, the fraction of the documents they appear in, and so on and so on, right? We'll explore the results a little bit further, right? We can look at what words appear in topic 12, right? So one of the things I kind of glossed over here is that I picked, by default, 20 topics, 20 groups of words of text that the LDA topic model is going to create, right? That's one of the things you have to know a priori is the number of topics you're going to have. So here we have, you know, the document fraction, the topic, the document frequency, the token score, and the actual word that appears. We can actually look at what these topics look like, and we print out the first 10 words of these things. Here they are. Here's topic 7, topic 8, topic 9, and so on and so on. You know, they might be meaningful to you in context. They might be just things you're going to use as a feature. And then we can take any given document and just easily plot what its topic distribution is.
Groups of words based on your Bayesian analysis, how does it know which token is the one it's going to show you?
These are just ranked in order of probability. Yeah. And I just say the first 10. Yeah. So everything is just ordered, right? You see the probability of this topic is this, probability of this topic is that, probability of words that. Yeah, cool. I'm just gonna, and then just generate some random colors here. And it doesn't plot for some reason. Great. I must not have pushed it. Great. I'm not online. Okay. We're going to stop right here. But essentially, what we did here was that we took a collection of documents, we streamed them, we tokenized it, everything was in parallel, we moved it to a format, Voelpel-Wabbit format, and we were able to just read off the results and play with the results and explore that. And that's actually a fairly, it looks trivial, but it's actually a fairly involved process if you're going to do it from the start. Yeah.
Do you work this way at all? It seems like kind of a way to kind of iterate through it separately in chunks versus
By work this way, you mean in the IPython notebook?
right.
Yeah, I do a lot of exploratory data analysis in IPython notebook. This isn't the way I write code, right? I'll write code in a standard, you know, like Vim environment. But this is definitely a great way to see things right away as opposed to having them pop up. Yeah.
What's the state of the library? Is it like a 0.1 or is it like sort of polished for release right now?
It's 0.2 state, right? 0.24 as of this morning or yesterday. So it's, you know, it's fairly well tested. I mean, everything is tested pretty much that we can test. So there's, you know, there's people who use it. I mean, it's definitely ready for use. There's not like any, you can pip install it and you can do this and you can do this and variants of this or aside, Voelpel-Wabbit aside, but you're basically good to go. You can take the streamers. There's a bunch of different types of streamers, file streamers, generic streamers, and so on, and tokenizers and things like that. And
A roadmap of stuff you want to add to it, or is it you're satisfied with what you set out to do?
no, I'm definitely not satisfied. You know, one of the things, you know, I wouldn't even know where to start of the things we want to add. I mean, there's a whole bunch of, there's some natural language process things that I'd like to make faster to think about. There's a whole bunch of database plugins, you know, database driver type things that there aren't any, right? There's a nice text file streamer, which allows you to just give me a base directory and let me do all these things with all the files that I find in the crawl. There's a nice generic streamer which says like, give me anything that iterates and returns text. That's an iterable and it returns something with a text key. Great, right? Whatever that might be. But there isn't something that says like, hey, give me an MySQL connection, right? And you know, because we have to, you know, you have to think about what does that mean to stream because of how MySQL queries are done. But there is a way to think about that. You can actually control the cursor. That's not written in Mongo, so that's a big thing that I'd like to do that I think is important. Ian, what do you think? What's like the next big thing you'd want to happen?
I don't know.
Okay.
No, but I think, yeah, database connections would be awesome.
Yeah. It's just you have to do it yourself now, and I think it would be a nice piece. Go ahead. Sorry.
Yeah, a couple of architecture questions. Something like the term frequencies and the IDF and who gets to your talk is be a classic Hadoop problem. Why did you decide not to use MapReduce for these things and to do it
the question is, what, sorry, I'm just going to repeat. Yeah, the question is why not go with Hadoop? Why not go with like a big MapReduce type of framework? And why use quote expensive hardware? The answer is that it's not expensive, the hardware we use, right? I think we're using, I built all these things on my laptop for the most part. I like to do the example of the big machine, but we never actually even used it, right? I mean, we was owned by somebody else, and we were no longer there, basically, by the time we could have used it. But the point is that all these big distributive system frameworks are complicated and very, very restrictive. Hadoop is restrictive in what you can do. And it also requires a lot of overhead to make this thing run. We don't do anything complicated. We just work with, we work with disk I/O, we work with basic memory, we work just within the computer. And a lot of these things that were done were we would create incredible overhead and many, many problems which are not necessary to solve these. That's really the reality. Hadoop solves a different problem. We don't have that problem. The scaling problem here is not Google. Scaling problem here is mainly stable. Ian wanted to say something.
In terms of roadmap or in terms of things to add, I think some integration with scikit-learn and examples showing so we have a nice sort of well played out example going through the LDA portion of Volpelwabbit.
Yeah.
What about going through some of the other Volpelwabbit pipelines? So Volpelwabbit does a lot more than LDA.
That's right.
And in all cases, the output format isn't a pandas data frame, which is what you would like here. So why not, if people can work with it so that the output of Volpelwabbit's linear models can be fed into a data frame, that would be great. Or just examples showing the output being fed into scikit-learn.
That's right. We added in the last release, there's we allow you to output the format to a SciPy sparse matrix, right? Which is what sort of the first step if you want to work, you want to be compatible with sklearn. However, that's just a first step, right? We don't have examples of that, and we don't have, there are going to be other things people are going to want with it. Go ahead.
So are those distributions features that already exist, and how do you, map the distribution from one set of documents to distributions to another set of documents?
So the question is about building LDA models, right? So basically, the model output is cached in a file, right? It's written to file. So you know everything about your semantic distribution, right? So basically, you can take a new document. I could have demonstrated this, but I didn't. You take a new document, you tokenize it in the same way, and you do a comparison, like basically a cosine similarity of its affinity to the topics versus the affinity of all the other documents to the topics, right? So then it's totally portable. It's just a file, as long as you have the bindings to read it. Yeah. Go ahead. So the two obvious examples. So for example, I had two examples, right? So I had the legal example, right? That was about 600,000 to 700,000 documents originally. Their size varied from So it was the legal data was 140 gigabytes. Yes, at the end. I can't answer I don't have a perfect sense of what the declassification engine database is, because it's always growing. But the different collections are, we're talking roughly the same, couple hundred gigs, 200 to 300 gigs if you're working with a particular collection or sub-collection. But if things go the way they're going to be going, they're going to be, the volumes are going to grow pretty much exponentially with these, because more and more is being released and more is being available to the researchers. Yep. Well, the number of features you have, well, that really depends on your choice of tokenizer. It depends on your choice of filter. It depends on your. No, you can't take everything. Well, I mean, so you pick so the thing that determines how you pick your features is partly experimentation, partly some natural language processing analysis, right? Some exploratory data analysis, right? So I don't remember off the top of my head how many features we had, but I had like we had in the legal 300, 400.
Yeah, and for this case, remember we took the topic weights as features. So we take, say, 50 topic weights and 50 metadata items and 200 other hand-chosen words, and those were features. No,
Go ahead.
I mean, these were domain expertise chosen words. So, I mean, remember, there's sort of two things we're talking about here. One is the LDA pipeline, which is where the features are the words, and you could have 20,000 different words. So you could have 20,000 different features, but it's a very sparse data set. And the other is after you come up with LDA topic weights, you can feed those in as features into, say, a random forest. But then you can't work with 20,000 features in a random forest. You're going to work with, say, a few hundred.
And the reason the reason you work with a few hundred is not because you throw out all the words, is because in that particular case we just had regexes, which stood for aliases of all the words we cared about, right? It's like it was just had more flexible things than stemming, right? Per se, we needed it for that particular thing. That regex file, right? The file of regexes used to create the features was done through exploratory data analysis as well as domain knowledge. That's why we're not talking about, there might have been 220,000 words or tokens that went into the LDA which produced 50 features, and then there might have been another 250 regexes which stood for God knows how many actual token words, right? But the actual feature set was fairly small. But it was flexible and representative in different ways of the corpus we were working with. Does that make sense?
It does, except that it seems that you take the most frequent features anyway, right? Because you would lose, like, you would classify this, you could use this to classify the clusterized data set, maybe, but not to find significant information, because significant features will be rare. They will not be part of your space.
I completely agree, but there is no reason we take the most frequent features, right? We take the features that are indicative of whatever it is that we're trying to do. So for example, you're trying to classify relevant versus non-relevant in the legal case, and you know what relevant means, and you have a training set, right? That doesn't mean you're going to take the most frequent words here and the most frequent words there, right? That's not necessarily true. You might take the words that only appear here and only appear there. Imagine you have a word that appears 50% of your relevant documents, it appears in 0% of your relevant documents, but only appears once in these because it's like Madoff, so you take that one, right? So there's there's no inherent process of how we build the feature set, right? That comes from the problem at hand, and I think it always has to come from the problem at hand, aside, maybe deep learning type of hierarchy, stuff. But that's not the problem here. Go ahead. One more question, and then you can just bug me afterwards. Sorry. I'm sorry. Could you repeat? Is there a disadvantage to using stochastic gradient descent type models? I mean, whatever disadvantage whatever loss of accuracy you could there's no inherent reason why a stochastic gradient descent optimized, random forest is going to be, or WOPO-WABIT LDA is going to perform worse than something else, right? But the reality is that something that is an online process is infinitely scalable, and that we need to have for these things to work, to not rebuild it for every data set, right? I think that we're gonna have to.
That's we're gonna have to wrap up at this point.
But you can ask me afterwards.
But yeah, let's give Daniel a round of applause. Thank you.